classification model, you can see very basic, same thing as we discussed before. So take the data, split into training and testing, X train, X test, Y train, Y test. So we do the train test split and we use an algorithm called logistic regression. So this is the new algorithm that we are using. We are using a new kind of algorithm called logistic regression. And we fit the model on the training data. We do dt.fit X train, Y train, and we do the predictions. This part is exactly what we talked about. And we also get the cross-validation scores. So why do we do cross-validation? Because remember, I told you that we should not trust the test accuracy. Okay, so we should not trust the test accuracy. So cross-validation is what we are using to get 10 different accuracy scores and take the average accuracy score. So we are doing cross-validation to generate 10 different accuracy scores and in turn find out the average accuracy score. So that's what we are doing as part of cross-validation. Okay, so that's the whole idea of what cross-validation is. Okay, so once again, so what is the nature of this model right now? The training accuracy is 77% and testing accuracy is 76%. So this is like a kind of an underfit model. It's not a very good model, but we can say it's a kind of an underfit model that we are getting. Okay, so you take some data, you build a model, and we are getting a kind of an underfit model where the training scores are low and the testing scores are also low. We're getting a reasonably underfit model right now, and we are trying to make it better. Okay, so we'll see how to make it better. But obviously, everything else that we saw here in the code is exactly what we saw. There's nothing new. The only different part is we are using something called logistic regression. The logistic regression is what we do the classification part. Okay, so the only difference is that instead of linear regression, we are using something called logistic regression. Okay, there are other kinds of algorithms that we also have for classification. So in this notebook, we will see what are the different algorithms that we can try out. What are the other algorithms that we can try out? You do not need to get into the theory, not needed, but understand the application. That is most important. Okay, so how to use, what are the things to look out for? Okay, because one of the things that I have figured out by taking these sessions and by teaching a large number of people over the years is, honestly, it doesn't help. Like only area where I've found it is useful is maybe to some instance in tracking interviews, where they sometimes ask you questions about, hey, what is X and what is Y? That's where all these 1 year, 2 year long university programs come in. But when it comes to the real world, when it comes to actual application, okay, I know of no data scientist who actually goes and thinks of logistic, hey, this is the math and this is when they apply it. You have the libraries with you, have the frameworks with you, you go and apply it. Because you have to understand, and you have to understand machine learning is a largely experimental domain. Given any data set, there is no way of saying what algorithm will work. You have to try it out. You have to build a model. You have to try out. You have to see what kind of accuracies you're getting, and only then you can be certain. Like let's say even yesterday's exercise, a concrete. There was no way of knowing in advance that hey, my data is having a non-linear pattern. There's no way you can say that. No way. Unless you can perform statistical tests, but generally you have to build a model. You have to experiment. You take the data, build a model, build a linear model. You saw you were getting 60%. You tried a different technique, you got 80%. You tried gradient boosting, you got 90%. Sorted. That's it. That's the way how we actually do it. Okay, so even by knowing the mathematics of gradient descent or knowing the mathematics of gradient boosting would not have helped you get extra 2%. You will still have to use Scikit-learn and call the model. Right? So again, you have to understand which are the avenues where the math and science is needed. Okay, unless you're in research, unless you're actually working at a class level. And that is also an important skill. As I told you, there are people who are working on, because these are open source libraries we are using, right? But sometimes you will want to use custom algorithms. You want to develop algorithms specifically for your data set, specifically for your problem statement. So maybe there are different variations of decision trees that you want to use with different loss functions. So decision tree algorithms use different loss functions. You want to use a different variant of a decision tree. You might have a different use case. You might want to build a different variant of a gradient boosting algorithm for your organization. So what you will do, then you are back to concepts of object-oriented programming. You will go to Scikit-learn because see, all these are classes, right? If I show you like, this is the same thing I was talking about a little yesterday. So if you go to gradient boosting, these are all classes, right? So somebody somebody would have come up with this algorithm. This is Scikit-learn gradient boosting regressor. And if you click on the source, you will see the entire source code. This is a huge class. Somebody had to write it, right? Look at this. You count the number of lines of code. Huh? This is 2,192 lines of code. Are we doing any of this? No, we are using it. But somebody has to write it, right? So two things. Somebody had to understand what is gradient boosting. Somebody had to, create the algorithm mathematically. Statistically, they had to do that thing. And then you need a developer to actually convert this into classes, right? So both are important skills, right? I'm not saying that this is not important, but my point is from an application perspective, this is useless. In the day-to-day work, day-to-day real-world application, you will not be, like required to understand what is the decision tree and what is the gradient boosting to solve business problems. That is a very different skill set. I know a lot of people who are very good in theory. They are brilliant in answering questions, but when you give them problems, they fail. You know, uh, Another very interesting insight I wanted to share, because these are all studied and tested strategies, right? Typically, people who do very well in Kaggle is a competition website. Okay, it's the same website where we took our data sets from. Typically, people who do very good in Kaggle, they are very good in solving competitions. They are very good in hands-on. A lot of hands-on is about getting the work done. I give you a problem statement. I don't care what you do, how you do, just solve the problem for me. Trust me, it's a very different skill. Okay, it's a very different skill. So you have to approach that from a very different mindset. So when you're solving real problems, when you're solving real competitions, your focus is on time. You don't have the entire day. Research is very different. Research is where the company is funding you for 3 years. But real production, the client is only funding you for 7 days. You have limited time, and in that limited time, you have to go and get a certain accuracy and get the job done. I don't care what happened, how it happened, what it is. Try different things. You have a limited amount of time. You have lots of constraints. You work within that constraint zone, and you get the job done. So they are very different skill sets. Okay, I just wanted to clarify that, because when you look at all of these things, right? When you look at all of these things, you know uh, this is a very different world altogether. So okay, so don't be intimidated. Like, although you were able to use gradient booster decision trees in the class, you were able to build the model behind the scenes. This is all that is happening, but you don't have to worry about it, right? So just wanted to absolutely clarify that part. Okay, yeah. Anyways, so moving on, this is the logistic regression model that I have used here. Okay, now next up, let me show you. We are trying out a gradient boosting classifier. This is a variant of a classification algorithm that we are using. Okay, just like we had gradient boosting regressor, similarly we have something called gradient boosting classifier. Okay, so this is like a non-linear classification algorithm. Just like we have gradient boosting regressor, which is a non-linear regression model. Similarly, we have gradient boosting classifier, which is a non-linear classification algorithm. N estimators will be a hyperparameter, but one key learning is that the model is little better. I think you can clearly see that compared to the linear logistic regression model, the baseline model, which is giving us 77, 76. If you see, the gradient boosting is giving us 83, 79. It's not great. It's not brilliant. It's not as high as concrete, but I think you will still say, we can still say that we have incrementally built a better model. This is a model that is working out better than what we had. Okay, so this is the incremental improvement that we are able to get here. Okay, now let's see what else we have. And what I'm trying to do in this notebook is I'm trying to clarify a lot of the classification concepts. Okay, the first part is good. We are sorted. You can see there's nothing different we are doing. Cross-val scores and all this is very similar. Now let's move on. What are the different ways we evaluate a classification model? Now this part is important. We talked about train accuracy, we talked about test accuracy, but what else? If you look at this particular exercise right now, what are we doing? We are effectively trying to predict, does the person have diabetes or does the person not have diabetes? Right? So, and if you go by the different steps that we covered, we take a data set, we take a training data, split the data into training and testing. On the training data, we build a model. And on the testing data, the mock question paper, as we call it, we evaluate the model. Okay, so we build the model on the training data and we evaluate the model on the unseen test data.